believe by its orientation, we will have to move from the north in a clockwise fashion to the line. And when we are doing that, clearly, we'll go past this 90 in our clockwise movement. You start from here, 10, 10, 10, meet the 90, and continue to meet the line. So our adaptation of 130 degrees is not out of place. It's well situated. Then we use that of C as well. C2, you need to start from the north, 10 clockwise. But you will see that as we are turning the purple line, this 90 will cross it. This 180 will cross it. Even 270 will go above that. So for a line in this environment, your bearings will have a value more than 270 but less than 360. So for this, we adapted 300 degrees. So we saw how we got our 300, meaning to go beyond 270 and then by this much. So that was with the whole circle bearing. Then we got some examples further. Then we move on to the quadrantal. In the quadrantal, we had our cardinal direction, which is two axes intersecting. And when the two axes are intersecting, they split the circle into 4 quadrants. So there too, we began looking at some examples, and one of them was this line, for instance. And we said, when this line is here, it is in the quadrant defined by 2 axes, the north direction and the east direction. But when you are also in this space defined by these 2, the language is always you start from the north, you turn an angle. So that turning should meet the line. And then that angle is, meaning that you cannot go this way when you are in the first quadrant. Because from the north, you should be heading towards the east. So we had it to look at. And I said, given the geometry and the fact that the line is aligned more towards E, it means it has gone past the center part of this space. So it's more than 45 degrees. And I adapted a 62 degrees as the angle involved. So the bearing becomes north 62 degrees east. Then we did it for this as well, OC. Then we did it for another one here for the third quadrant, another one there. So when you are in the reduced bearing notation, we use the quadrant. Quadrant between north direction and east direction is 1. Quadrant between south direction and east direction is another. Then we began to look at switching from one into the other. How do we deal with the issue? The first that we used as an example was AB. So we were looking at AB, 89. Clearly, this one, we also spoke about the differences. When you're in the whole circle, it's only numbers with your unit of measure, degree or degree and minutes, but no letters. Understand that. No letters for the bearing, not for this. This one is the line, the definition of the line, AB. But the reading of the bearing is just 89. So in that state, then we have whole circle. How do you find the corresponding quadrantal of such? You look at the orientation. 89 is between this direction and that direction. Having fused the two, the circle here is supposed to help us with the whole circle definition. The four cardinal directions are supposed to help us with the reduced or quadrantal bearing definition. So with our 89, and then superimposing it with the cardinal, we'll see that the 89 clockwise is from here to this point, close to the 90 direction. But when you superimpose the cardinal, it is between the north and the east. So it is in the quadrant north going to east. How do we call out bearings there? It's north, alpha, theta, east. This alpha is the angle the line is making with this north. So in this case, AB is here. And the angle AB is making with this north pole or north direction is 89. When we go for the quadrantal, it becomes north 89 degrees east. North 89 degrees east. So that was what we had as one of the examples that we dealt with. Then we had another one. I think I did clean some of them, but there was another one where we had OD equal to 205. So 205, the principle is the same. What it then means is that from the north, we'll turn clockwise until we get 205. Now, when we turn and we get to this line, it's 90. We continue to move clockwise. We get to this line, it's 180. But we are looking at 205. So the question is, having gotten here from there, how much do I need to add to 180 to get 205? And the answer as deduced last time was 25. 25 units. So when I add the 25 units, then I'm going to have a scenario like this, where the line is supposed to come out from here. Something like this. And then this angle here should be equal to 25.
Is it OD? GOD?
Come again.
Is it?
For the example, I stated this one as AB because I was looking at the line AB. But if your line is OD, then definitely the label here should be O. And then the one at the end here should be D.
D. And O.
Is it clear? Yes.
Yeah. Hello.
Yes.
Please, is it OD?
Yes, OD.
Is it OD?
Yes, it is OD.
Yes.
Where is the O and where is the D?
No, you're not listening to what I'm saying.
You said? Hello.
Yes.
So I was saying that the OD, which side is the O and which side is the D?
I was explaining and you were not listening. I said
Oh,
we
not that I was
started
not
with,
listening.
if you were listening, you would have seen it by now. But I said AB.
Mm-hmm.
We started our example with AB. And when we started with AB, this is
Mm-hmm.
how we drew the line. We drew the line here, A here,
Yeah.
and B here.
Yeah.
So when we go to OD, what it means is that if it was only OD you are working with, O will appear here, and D will be at the end of the line here. Unless you are not seeing the screen. So do you see the letter A?
Yeah.
Are you seeing the letter A?
Yes.
Yes,
Yes,
Yes.
yes,
sir.
yes.
Yes.
Okay.
Yes.
Yes.
So your O will appear here, and your D will appear here.
Okay.
Hello.
Thank you.
Hello, Doc.
Yes.
Please, can you use like AB, or can you use the same origin as A for both B and D?
No.
Okay.
It is question specific. What I'm doing for you is illustration. If it's question specific, you draw all of them, their sketches differently. But I said at the beginning, and that's why at times I am not happy the way you people respond to lectures. You don't listen. I said at the beginning that a line is defined by the first letter and the second letter. So what it means that I have stated two different lines. So if you want to superimpose, you will have a challenge. But I've also explained how it will be done. So if you want it to be clean, you do AB separate and you do OT separate. Because the line
Okay.
definition is on the two letters. This is the start. If you remember, I spoke of bearing. I said there should be a source point and there should be a destination point. You remember?
Yes.
I told you there should be a start point and there should be a finish point.
Yes, Doc.
So definitely, once you are seeing one example as AB and another example is OD, but you are looking at the principle, the better of the two is to do the sketches. But I cannot afford that because it will waste time trying to draw both listen. That's why when I'm talking, I add the differences so that you know why I've left it or used it the way it is. But your notes should help you get that clarification so that you don't go back to get yourself confused. Is it clear now?
Yes, sir. It's clear.
Good.
It's clear now. Yes, sir.
So this angle here, beyond the 180, for us to get 205 should be 25. Because 25 plus 180 will give us 205. Here, the language is you turn from the south towards the west. So the bearing of this line, OD, this one is whole circle bearing. This one is WCB. But the same thing in quadrantal will become south 25 degrees. West. So this one is talking about reduced bearing or quadrantal bearing. Is it clear? So we had this and we created another scenario here. And I think I even one of them I gave it to you as an assignment. I don't know whether we got it. So all of these were examples that we expressed. And then the idea was for us to look at how we go back and forth. In the last one, I think I gave one which involved the degree and then one subunit, the minute. The degree and the minute. And in the whole circle, the line was, check your mic, check your mic.
Madam Abena, please mute your microphone.
Sorry.
All right. So there was one which I quoted as 161 degrees 40. And there's a green line for it. So it's supposed to be Q something. I think the other letter I've mixed up on it. Then there was one that I stated as PK with this. But interestingly, the PK is a reduced bearing to this same definition. So I don't know what happened here. People were giving suggestions. I think this ones were more of the suggestions. So eventually, these ones have to go. Some were people's suggestions. Then let me make it more clear, and I'll change this one. Then right after I have Q here. So let me say we call it QP. So let me use the pen and then write it as QP. So P is here. So we are saying that if the line QP is stated as 161 degree 40 minutes, one bar. This format is whole circle bearing. Oh, my space is small. This is trouble. All right, so this is supposed to be whole circle bearing. So that is with 161 degrees 40. And when you plot, you'll see that 161 is more than 90, so you'll be in this section. If it is the whole circle bearing, you don't expect the letters. It should be in the numbers 0, 90, 180, 270. When you're in the quadrant, then you have the letters north, east, south, west. So in the first one, for the first implementation, the north, the east, the south, and west is not present. It's only your numbers. So whole circle says from the north 10 clockwise. At the time I'm here, it's 90. The figure is more than 90. So I keep going. I cannot get to 180 because 180 is more than this figure. So I end somewhere here, generally. And when I end there, it means the line will appear there for the bearing, QP. And alpha will be 16140. To go to the other side, I impose the north, south, east, west direction, the cardinals. And as soon as I do that, my line is found between the south and the east. In this quadrant number 2, the language is south.
Hello, dog.
Yes.
Dog. Please, with the 40 there, which the 40 there represents what?
The 40 there is the minute.
Please, I'm not a little clear with
We have said earlier
hello.
that when it comes to angular measurement, the degree is the main unit, but there are 2 more subunits, the minute and the second. So anytime you see this writing, the 0 here is standing for the degree. If there's any add-on, the chances are that it is either representing minutes or minutes and seconds. In this case, it is 40 with 1 tick, so that is minutes. There are no seconds there. If I had wanted to write a full expression of this, it would have been 161 41 minutes, 40 minutes, and then 0 seconds. So this would have been the full label in terms of the 3 units of measure. And they are all talking about the angular measurement. So that is the degree, minute, seconds notation. Most often, questions may not have. How will I what?
How will you determine the 40? Either it will be 40, 30, or how will you? We did it last month. Since it escaped me, So the 40.
Well, for modern day instruments, you should be able to measure with some higher systems. But if you are measuring with the protractor, it can only be an estimate, because on the protractor, every tick is a degree. Every tick is a degree. So if you are using the protractor, you will not be able to plot 161 degree 40 minutes. You can at best plot or draw 16130. And the 30 comes from the fact that from one mark on the protractor to the next one, if this is 1 degree and this is 2 degrees, then when you are here, when your reading is here, when your reading is on the middle, it is half of a degree, 0.5. And half of a degree is 30 minutes.
Okay.
So when you are using a protractor, that's the best you can measure. But then for more precise
So if
instruments
it is
like
on the
total
1,
stitching,
if it is on the 2,
if what is on the 2,
I'm saying that if the reading is on the second, it's not in the middle, but it lies on the 2, then it means 60.
technically in between 60, but what would mean is that when it's on the 1, you're talking about 1 degree to stop. If you want to write for the minute, it will be 0 minutes and 0 seconds. If you are in the middle, it is 1 degree, then half. The half is 0.5 of a degree, and that is 30 minutes. But there's no seconds, so you can add another 0 here and put the 2 back. But usually when we don't have data for the seconds, we don't write it. It doesn't mean that you cannot write it. You don't write it. So when it's when you are here, it is 1. When you are here, it's 130, 1 degree 30. When you are here, it is 1 degree 60. But usually, I gave you some conversion. We don't usually leave it as 1 degree 60 minutes because there's a scale for converting minutes to degree. And I told you that 60 minutes is 1 degree. So although it is possible in terms of mathematics to write 1 degree 60 minutes, and you are not wrong, this will be converted to 2 degrees. So if your line is lying on this one, the outer one here, it's on the 2, so you call it 2 degrees. But if you are still making reference to the first one here, this one which is on the 1, then when you are here is 1. When you are here is 1 plus half, and that one becomes 1 degree for 30 minutes. But when it gets here, you cannot say 1 degree 60 minutes, although it's not wrong. You would have gotten to the next whole number, so you have to mention it as 2 degrees. Is it clear now? All right, so we move on.
So the line you went off shortly.
Hello?
Yes, you went off shortly.
That's done.
All right. So we proceed. So now we see now we move from one system into the other and vice versa. And we even did some calculations down here where when we're coming here for the second part of the answer, which was 18 degrees 20 minutes, we wanted this angle here. Because when you're in the quadrant, you start with the south and head towards the east, as in this definition. The alpha here is the angle involved. So when you take off from the red and move towards the line, which you have it in green, this angle here has to be resolved for us to be able to quote correctly the bearing. So to get the angle, we can use this data to still get the angle. Why? This arc here, this green or off green type of arc plus this small space here should be 180. So if that is the case, then it means 161 degree 40 minutes plus something should be equal to 180. So who is that something? We go and subtract this value from 180. And that is the mathematics we did here. So I think apparently we did this one rather first. This was given, and then we found the corresponding. So I think the earlier one, we had done the whole circle to quadrantal. So in this one, the calculation here suggests that we rather had this, and we wanted to find the corresponding whole circle bearing to it. Is that okay? So
Yes, sir.
if we're given the 1820 and we want to find the whole circle, we need to subtract from 180. So we came here and we had a 180 minus 1820, and we said the 20 is the minutes. So when you are writing the 180 is for degree only, no minutes. So what you can do is to replace the minute side with 0. So when you do it this way, then how do I subtract the minute side? Go and borrow from the degree and come and spread it here. But when you borrow, note that 1 degree is equal to 60 minutes. So when you take 1 from here, you'll be left with 179. And then that 1 degree will be converted to a minute, and that's a 60 here. So you end up with 179.60, which is the same as 180. But then it's more comfortable to use here because there are 2 entities we are subtracting from. All right. So that is how the calculations is done. And you need to do a lot of practice on your own going forward so that you can get used to the various units or the various issues involved. So that is it. We try to make progress from here. The last thing that I had wanted us to, and the first for today's lecture, is to look at chain surveying and the diagram that I have displayed up there that I'm currently sharing with you. When we spoke of surveying by instrument in terms of the classification, the chain surveying was one of them we mentioned. So we need to have an understanding of the chain. The chains that we use for chain surveying and for distance measurement, they are of 2 forms. I gave you a work with respect to that. To go and find out of these 2 forms, one name Gantt's chain, the other name engineering chain, engineer's chain. Have you done that work?
Sir, please come again, please.
Are you? All right.
Cartography.
So there are 2 chains that we use for survey and distance measurement. One is called Gantt's chain, G-U-N-T-E-R, Gantt. So we usually call it by the name Gantt's chain. Then there's also another one called engineer's chain. And I said, if you have done the assignment, one of them is longer than the other. One of them is longer than the other. I even shared a slide with you on one of the discussion where we're looking at some of the instruments. Week, I think 3 or week 2. With 2 material. I shared that one with you. So when you are dealing with the chain and using the chain for survey activity, we can say you are involved in chain surveying. One of the fundamental things of chain surveying is that you cannot measure an angle. You cannot measure an angle when you are dealing with chain surveying. Angular measurement is not possible. So when there are issues involving angles, we use the principle of triangulation. We try to capture the thing by a network of triangles, a network of lines forming triangle. That is the idea, because we cannot measure angles when it's about chain surveying. The diagram that I've displayed there is a sketch of a field work involving chain surveying. Sketch of the field work involving chain surveying. Thank you for those of you who have done the assignment and you are sending your notes. I'm seeing them in the background. Well, if you have done it, you should be confident in whatever that you have sent. If you have not done it, it will be hot. So that is with the two types of chain, and then with chain surveying. In surveying, every point you stand at to perform an activity or do a work is called station. Station. S-T-A-T-I-O-N. So in the display that I'm sharing with you currently, the letters A, B, C, and D represent stations. They represent stations. The line from A to B, the line from B to C, the line from C to D, and the line from D back to A are called survey lines. Survey lines. When, because of their distance, they are the more focused, the more focus of the activity, we call them the main survey line, like this one. It's labeled main survey line. On the ground, if you want to realize it, you have to tie a rope along this path. Then you will see the survey line. It is not always that we implement a physical evidence of it. We can still implement a virtual evidence of that. They are called main survey lines because they connect your main stations, A, B, C, D, and back to A. But there's another one we call the baseline. The baseline in any chain survey work, and even generally in GPS and other work. The baseline is the longest possible line within your area of survey, like the picture I'm giving to you. This is a main survey line. This is another main survey line. This is another main survey line. I'm talking about A going to B, the distance involved. The distance, the direction is the survey line. B to C, C to D, and D back to A. So, having understood that there are four main lines, survey lines here, AB, BC, CD, and DA, we call that the main survey lines. But watch line B going to D. Line B going to D is also a survey line, but it is called a baseline. Why? Because it is the longest running line through the area of survey. The longest running line. So if you are computing for distance, BD is longer than AB. BD is longer than BC. PD is longer than CA. So I've mentioned survey line and I've qualified them. Main survey line. It connects your main stations. Then we have the baseline, which can connect the main station, but it's across the area of survey. The main survey lines here, they connect the stations direct and they give you a kind of boundary definition of the survey area. So A to B, B to C, C to D, D to A, the main stations or the main lines. But there's another one which is through the survey area and the longest, such as from B to D or from D coming to B. This is called a baseline. So the difference is that the baseline is the longest survey line that runs through a survey area. Now, when A, B, and C have been surveyed, so this is the area we are interested in, and we have placed stations close to the edge of the area to define our space. So if A, B, C, D is your station, any other place you occupy in the survey inside the survey area, like S2, S1, and T1 are called subsidiary stations. I told you that in survey, when you say something is called a station, then it means the surveyor or whoever was doing that work stood at those points to do some kind of observation, reading, or survey work. So A, B, C, D is main stations. S1 and S2 are called subsidiary stations, meaning that they are minor considered. They are not the main actors when it comes to the station, although they are also stations. Good. Now, when we connect the main station to these subsidiary stations or any other stations within the survey area to use as check lines or tie points or tie lines, then they are supposed to help us pick additional information to strengthen our work. Note that I said the chain, you cannot measure angle. So whatever that you do on the field, you cannot be seen to be measuring angle. It's not possible with a chain. So we try to connect our survey area by a series of triangles and then use the triangles to pick details. How do we pick details? In chain surveying, and that is very, very important. We pick details in chain surveying by the concept of offsets. Offsets. O-double-F. S-E-T-S. If it's singular, it's offset. When it's plural, it's offset. So my point is that we have an area to survey with a chain. This is a depression. This is a building, another building, another block. So let's say we have about 4 items, or 5. There's a road also here. Now, to help us survey MP details, we have the main survey line as A going to B, B going to C, C going to D, and D coming back to A. In this area to be surveyed, when I connect, because I'm still looking at connecting lines by a series or a network of triangles. So you see that this depression has been taken care of by this triangle here. When you take this building, this triangle here is taking care of that. When you are here, this triangle there is dealing with that. And when you are here, this other triangle, either this way or this way. So we've mentioned the main survey lines. They connect the stations. That's their duty, that's their work. Then we also have baseline. And the baseline is the longest survey line through the survey area that runs uninterrupted, meaning that nothing blocks it. That is the baseline. But you can have other lines like check lines, which you use to check whether the measurement done by some other point are correct. Or you can also use it to tie. C1, C2 is called a tie line. Why? They are supposed to help us trace position of B. Later on, if you want to draw the sketch or plot the points. So the idea is this building is supposed to be picked from this triangle. This depression area is supposed to be picked from this triangle, CDS1. This building here is supposed to be picked from this triangle, AS2, B, and then back to A. The building and roads here are supposed to be dealt with by the triangle BCS1 and back. Good. So these are the issues that usually borders on chain surveying. Now, how do we pick our details? And here, I want you to watch closely what I'm going to do with the diagram. It's part of the culture of a chain survey. We pick our details using what we call offset. Now, what is an offset? And what are the types of offsets? An offset is basically a distance measurement from a survey line that is used to fix or locate a feature or a detail. In surveying, when somebody says a detail, it just means an object of interest in the survey area where measurements are taken from or taken to. So the building, this one, is a detail. And the corners of the buildings are also detailed because they help us to know how the shape of the building is. This rectangle is also a detail, but there are points that are the vertices are also equally detailed. So when you hear that I am detailing, as in the survey activity, it means you are running measurement to points of interest in the survey area so that you can show them graphically on paper. Good. So how do we pick our details? In terms of the offset, there are two forms of offset. So note it down. One is called perpendicular offset, and the other one is called oblique offset. Perpendicular offset and then oblique offset. How are the spellings made or written? Perpendicular is a term in mathematics, and I'm sure you've heard it as well, where a reference to another line of reference is at 90 degrees. So perpendicular, PEN. So we have it as perpendicular offset so our perpendicular is spelled as PERPENDICULAR. Did you get that?
Yes, sir.
Doc, please, I didn't get the
So,
second offset.
Yes, Doc. Yes, sir.
so we have a perpendicular offset, and the
Oblique.
second one is oblique at an angle. So I'm going to show with a sketch the one that will form perpendicular offset and the one that will have to be called oblique. The oblique is OBLIQUE. Did you get that? OBLIQUE. Let's go to our diagram. For example, let me zoom in to this latter part of our sketch for the sake of the explanation. All right. So we said A is here, B is there. So when you travel along this line, it's your main survey line. Now, in our traveling, when you say travel, it's measurement. When I put a chain or a tape to A, and I drag it on the ground to this point, where distance measurement to pick this point here is 90 degrees, I'll call this measurement perpendicular offset. So let me try and see how I can incorporate or introduce a perpendicular offset to the analysis. So let's say from here, I measure from here all the way. I'm still on the survey line. Sorry about that. Good. Suppose this distance along the chain or survey line, I get to a certain mark, let's say 40 meters. And at that 40 meters, I'm able to pick this end of the building. I pick the end of the building, a distance measurement from this position. So this is what we call my main survey line. I moved from A, it took me a distance of, let's say, 40 meters. By the time I'm at the end of the 40 meters of my tape, I can pick this corner of the building. Let's call it, let's say P1. So you can have P1, P2, P3, P4. I can pick P1 from this line at distance 40 from the start A, so that when I read from this position to the P1, let's say I have 2 meters. The 2 meters will be called the offset at chainage 40 meters. The chainage being the distance from A to that point where I read off this one. Your 2 meters and the measurement will constitute what we call a perpendicular offset. Why? The measurement at that point was at 90 degrees. The measurement at that point was at 90 degrees to your survey line. And we said an offset is basically a distance measurement to a detail from a survey line. So I moved from A and got to distance 40 meters. At that point, I could reach P1 by making a distance measurement, which would be 90 degrees to my tape. So all this analysis that we are talking about, there's one tape that is going to run from A all the way to B, sorry. And on that tape measurement from A, when we go to 40, we can pick this one at 90 degrees, which will be done with another tape or chain. Because in the chain survey, you cannot bring in any other instrument apart from the chain. And the chain cannot measure angles. So we always have to find a way of using the chain, whether you are going to increase your number of chains to be able to achieve that or whatever. But that is the nature of the chain survey. You cannot measure angles. So everything will have to be done as measurement from the chain or tape. So P1 will constitute a perpendicular offset. So that is the nature of what we call the perpendicular offset. But you can have an oblique offset if in the same analysis, in my quest to capture P2, which this time is here, if I want to capture P2, so moving from A to 40, I capture this. Maybe when I move to about 60, I'll be here. I'll be able to capture another 90 degrees off. That will constitute the perpendicular offset. But if I don't do that, and I get to a reading, let's say 50, somewhere here, away from A, 50 somewhere here, and I pull a tape to try and measure here, I'm trying to measure from P2 onto my line. But clearly, this is an offset, but this offset is not at 90 degrees to my survey line. This one is at 90 degrees to my survey line. This one is not. So if I measure this, and for instance, I've got something like 3.5. So that's 3.5 meters. This will be an offset, but it will be an oblique offset. An oblique offset. This is a perpendicular offset. Why? It was a distance measurement to locate a detail at 90 degrees. That is where the stress is. At 90 degrees to your survey line. But in the case of the oblique offset, you are trying to locate details, but the measurement was not at 90 degrees to the survey line. Is the explanation clear? Good.
Yes, sir. That's
And
correct.
Yes,
and if you
yes.
have your hand up,
Yeah.
I'd like to know whether this oblique offset really makes a particular angle from the survey line.
in the first place, yes, it makes an angle, but you cannot measure that angle because you are using a chain. But physically, we can tell when an angle is 90 and when it's not 90, isn't it?
Yes, please.
Uh-huh. So the idea with the chain, note that this was what they had at the time, and this was what they were using at the time. Now we have sophisticated instruments like the total station and other things that can turn and give you angles. But way back then, we had only the chain. So their smartness is what led to this kind of concept and ideology. So yes, when it is 90, you are supposed to meet at 90. You can always create a 90 with your hand, with your body, with two papers meeting, with two pencils meeting. It's easier because we are used to right angle triangle. But for the non-90, it's difficult. So when we say it's oblique, there is no particular angle stated. But all that we are saying is that it is not 90 degrees to the survey line.
Thank you, Doc.
Good. So the main difference between the two is that while the first one, when it was perpendicular, we were measuring from the survey line to the detail at 90 degrees. In the second one, we are not assured of the 90 degrees. It's not there. But we also cannot measure angles, so we don't care. But what is important is we should be able to get our reading. So to finally be able to plot in the office, because you cannot deal with angles in the office, when you are dealing with oblique offset, you cannot measure only one and leave the field with that only one. You will not be able to plot it. Note that I said you cannot deal with angles, so you cannot plot with angles. But you can construct. So this is what the surveyor will do. Having read from here, let's say the distance from here, I'm talking about the same thing, the distance from here all the way there. Let's say the distance from here, this time around was, let's say 50. The first one we got 40 to pick this one perpendicular. The second one we got 50, but it is oblique. When you take only this one and go home, you will struggle to plot. So a smart way, because you cannot plot angles, but you can construct them. The smart way the surveyor will deal with this issue is that he will take another measurement, let's say a distance, a third distance, somewhere here. Somewhere here. He will take another measurement for somewhere here and go back again to this one, like this. This will constitute another oblique offset. But then the combination of this one and this first one will form a tie. T-I-E. To form a tie. And you'll be able to use the compass in our math set to tell us where P2 is exactly, using this data and this data from this position and that position. So what will happen is that when he goes to the office, he will move from A and get to 50, open 3.5, put a compass here from the math set, and then you construct an arc like this. Then you will move to this distance. Let's say this one is 68 meters. You will move from A to 68 meters. Open this length. If the length is, let's say, 1.5, you will stand here, open 1.5, and construct another arc this way. Then the intersection of the two arcs will tell him the position of P2. In the case of the perpendicular offset, it doesn't need that. The one data and the perpendicularity is enough, because perpendicularity is 90 degrees, it's exact. But in the case of the oblique offset, it is not 90. But you cannot plot with only one measurement. So when it gets here and does an oblique offset, at some point in the survey, when it gets here, you come back and do another oblique offset. So he needs to read 2 oblique offsets. Then he can come to the office and construct using the intersection of the arc from the 2 locations. He will stand here, construct with 3.5. He will go and stand here, construct with 1.5. Where the 2 meet, that is P2. So later when you reflect, you see that when you want to use oblique offset, you have to be doing more work. When you have to use perpendicular offset, you have to be more accurate. That's the difference between the 2. Oblique is not ensuring 90 degrees. So wherever you decide to start and go in that manner to take the measurement for an oblique, it's allowed. But you cannot do only one and come to the office. You have to do 2 from 2 different positions. So you have 2 measurements. They are all oblique. And when you come to the office, you construct an arc with one, construct another arc with the other, and the intersection of the arc gives you the position correctly to define P2. But you needed 2 measurements because you are using the oblique offset method. If you are using the perpendicular offset method, then you have to ensure that the distance that we got as 40 from this, that is the location where you can get 90 degrees away, a distance of 2 meters. If you have ensured that, and that is what we talk about accuracy, if a surveyor, you have to, there's a way we detect that. We will not be going to that, but there's a way we detect that. So you have to ensure that you have detected it rightly, correctly, then you can measure. But if you don't do that one too correctly, it will lead to errors when you come to the office and you're plotting. So what is the story briefly to our chain survey? Chain surveying is a surveying that does not have the ability to measure angles. So in any chain survey, no angular measurements are done. For a chain survey, an area you want to survey, first you have to locate stations that will form a kind of boundary around the area you want to work. In our diagram, A, B, C, D is the station. Distance measurement with the tape from A all the way to B is called a main survey line. Another one is found between B and C. Another one is found between C and D. Another one is found between D and back to A, as our diagram is suggesting. Beside the main survey line, we can also run survey lines inside the survey area. So for instance, A to S2 is a survey line. S1 to C is a survey line. D all the way to B is also a survey line. But inside the survey area, the longest possible line you construct or draw or use between the stations is known as a baseline. The emphasis is on the longest survey line running through the survey area. Running through the survey area gives you a baseline. Stations that are introduced in the course of the survey inside the survey area to enhance and make measurement easy are called subsidiary stations. Subsidiary stations. So in our diagram, S2 and S1 are stations, but they are stations for our measurement, and we call them subsidiary. T1 and T2 are also stations, but we are giving them a special name, T1 and T2, because they are being used as a tie. A tie is an introduced network of lines to form triangles to help you fix your stations. So T1 and T2 are measurements from B and A to accurately fix B properly on the ground. So when you tie, it means you have more than 2 readings to that particular point, and it's supposed to help you fix the point. So we've heard of survey line, we've heard of baseline, we've heard of subsidiary stations, we've heard of tie points, and we also heard of tie lines. Then we came to the measurements that we employ to pick our details, to pick our objects, to read to points of interest in the survey area. You are using the chain, and that is the only instrument you have. To do that, we use a concept called offsetting. And an offset is basically a distance measurement from a survey line. There are 2 forms of it. One is called perpendicular offset. The other one is called oblique. In the case of the perpendicular offset, measurements are made from the survey line to the object of interest. In our sketch, I use P1, one of the corners of the building. So I want to measure to that corner, but I do the measurement in such a way that the distance 2 meters obtained from that point is at 90 degrees to my survey line AB. Where did it occur on the survey line? 40 meters away from A. So when you come to the office and you are going to plot, after the general sketch, you will go and stand at A. Move a distance of 40 meters along the line AB. When you get to that point, you turn to the left and read a distance of 2 meters at 90 degrees to the survey line. So that 2 meters distance measurement, that helps us to get P1, or that helps us to be able to locate P1. But it was at 90 degrees to my survey line. It's called a perpendicular offset. But we can also have an oblique offset, as in the case of scenario number 2. Scenario number 2, we did 2 measurements. Away from the A up to this point, it was 50 meters. We used another tape to connect P2, and the distance was 3.5. So it's an oblique offset. So I cannot take this to the office. I need a second one. So on the same survey line, I moved to about 68 meters from A. 68 meters from A. And I come back to connect to P1 with another tape, a P2 with another tape. The distance involved was 1.5. These 2 readings are called oblique offset because they were distance measurements to the details, which are calling P2. But unfortunately, they were not at 90 degrees to your main survey line or survey line involved. So it will constitute an oblique offset. Because I'm not measuring angles, you cannot, and it is not possible, to only read one oblique offset and end the measurement in the field and come to the office, hoping that you can plot. It won't work. How do I plot a detail using oblique offset? I demonstrated that to you as well. You will draw your survey as you have captured them from the field in your survey or your plot table. Then, starting from A, you move until you get to distance 50. Then at distance 50, you fix a compass here with a pencil or the other end opening a distance of 3.5. Then with that distance of 3.5, you construct an arc. So compass is here. Open the pencil to 3.5. You construct an arc. Then you move to distance 68 along your chain, your survey line again. And then you go and construct another arc. So from here, you constructed an arc. From here, you have constructed another arc. The intersection of the two arcs will tell you where P2 is. But the measurement, 3.5 and 1.5 are all known as oblique offsets. Please, is it clear?
Yes, sir.
Yes, Doc.
Exactly.
Good. So briefly, this is how simple I want us to look at the subject of chain surveying and how it was applied. In fact, there are even methods of how you do the booking and how you record
Sir,
your
please.
measurement.
Hello, sir.
Yes.
Sir. Sir,
Yes.
please. My data got finished and I ran to get some. So I didn't get all you did. I joined a few minutes ago. I didn't get all you did. In fact,
So you may have to rely
I
on
don't.
your rep to get the recording and then you play it back. I've told you that we are working with time. So when you have such challenges, they will impact. But fortunately, we do the recordings. We have uh, group leaders and what have you. So talk to them and get some of this information, and then you play it back and you listen. Other than that, maybe you may have to form sub group discussion groups. Then you look at some of these things because you cannot deal with all those issues. So delay already the time is not enough. But that is the challenge because if we don't get the issues right about timing, about data, about those things, we will run out of data like you have done. It is not a nice thing. You want to rush and go and get some. By the time you come, community is gone. And we cannot always be coming back. So I'm sure we can get the playback or we can get the files and then work with them and we should be able to recover where we want to. Because each step of the way, as I was explaining, is quite important. And we cannot stand at the same place doing the same thing because of time as well. So I will request or I will suggest that you talk to your rep and see how you can get the recording. All right. So we continue. So that is basically about chain survey in the simplest way. There's a way to book it, and there are some other principles, but I don't want to include that one here. For instance, you see that we are, in this case, our object was on the left of the line AB. What happens if the object is on the right? All is shown when you are doing the booking. So in the booking, there is a certain line you will draw for your main survey line AB. And then information you captured on the left will be recorded to the left side of the line. And the information you captured to the right will be recorded to the right side of the line. And that is how your survey book and your drawings and your bookings will be done. So anybody who takes your survey book must see line A to B and the information that were recorded. I'll put down a picture of some of the recording that have been done, but I'll not be including that in the discussion for now. So let me see if I can quickly pull down. All right, so let me take this one off and bring that one in, just to show you how the booking is done. But we are not discussing that for now. All right. So look at this survey, for instance. The area of interest is this space. It has this, I think it looks like a tree. It has this building. It has this path or road. So the area was captured with the main stations A, B, C, D. Now A to, oh sorry, it's A, B, C, D rather. A to B had a total distance of 63.4 meters. And this has to be captured, it has to be measured on the ground. B to C was 75.8. C to D was 80.4. And then D back to A was 72. Then inside the survey area, B going to D was 79.8. So this is the survey area. This is where the work is being done. And it is the longest distance within the area. So for the survey and the area, this distance BC or BD, sorry, BD will form what we call the baseline. But distance A to D, distance B, A to B, B to C, C to D, they are all main survey lines. And their distances is what will be recorded. Then this detail was picked when you are moving from A to B. So when I'm moving from A to B, this detail is on your right hand side. This detail is on your right hand side.
Barbecue.
Say.
So when you are moving from A to B, this detail here appears to your right. But at the same time, if you are working on this baseline, this detail will appear to your right again when you are coming from here. But if you are doing analysis from D to B, this feature will appear on your left. So going down, this is how the entries are done. You have a double line to show your movement from A to B. So this is the A. And then line begins with A down and then it ends at B. So that triangle there is showing the station. The same station is here. But you see the measurement. As you are moving, you leave a space in there to write your measurement. The offset, this one is to your right. But the tree position is to your left. This is a road crossing your chain line. So when it's crossing your chain line, it is written at the middle where the roads are crossing. All of these that you are seeing in the middle here are distances. So from the station, this is 10.5. The first reading was done. 11.2, the second reading was done. 15.7, the third reading was done. But they were done to capture information to your right. So you will sketch the object and then you place the measurement on them. So 4.5 is the perpendicular offset at chainage 10.5. The chainage being the measurement on the chain line. 2.8 is a perpendicular offset for this corner of the building at chainage 11.2. 4.7 is a perpendicular offset at distance or chainage 15.7. So as you go along, you observe in the field. Those are on your right, you pick. Those are on your left, you pick. When you do it in the book, those on the right must be shown, the sketches must be there, the measurements are placed against them. This shows that moving from A to B, this feature was on my right, but this feature is on my left. And every one of them you need a chain distance, you need the perpendicular measurement. So these are examples clearly of perpendicular offset. I don't think there's an oblique one. And this one, it is cutting the chain line. So it is a line, but you are drawing it as 2 bars so that you can put the readings in the middle and put the offset onto the right or left, depending on where the object is. But in this case, which was a road, it was crossing it exactly. So it doesn't have an offset. It rather have the chainage or the distance measurement on the chain line. So this is just as a way of showing what is happening. And you see the final distance, 63.4, which was up there, 63.4. So what we're seeing is from here, there was this one, and there was that one, and there was a road. From A, there was this one to the right. There was also this one to the right, and there was this one to the left. But all of them, as you go, is distance measurement from A, distance measurement from A, and then you capture your offset. So from A, 10.5, first reading, 11.2, second reading, they are going to the right. 15.7, third reading to the right. This kind of measurement are perpendicular offsets. So most often the surveyor would like to do perpendicular offset. Why? That one, he needs only one measurement. If you go for oblique, you have to do 2 measurements, which may be a waste of time or a time-involving activity. So if you can do it from the perpendicular, most of the data will be captured with a perpendicular offset. Please, is it clear? Good. So that is with a simple introduction to one of the old techniques that surveyors were using for survey measurements, chain surveying. We've spoken about the principle. It depends on triangulation. So the whole survey area, we try as much as possible to connect the stations and to connect with other lines to form triangles. And when you are moving from one point to the other, you look at your right and your left for details. And you capture these details by distance measurement from your survey line. When this distance measurement is done at 90 degrees to the survey line, they constitute perpendicular offset. If they are done at a non-90 degree angle, they constitute oblique offset. So that is where we bring the end of our discussion on the chain survey. On the chain survey. So we hang it there. The next survey technique I'm going to describe or talk about is traversing. All right. Did you bring your master protractor and the things I told you to bring? Hello.
Yes, yes.
Yes, sir.
No.
All right. Good. So I'm going to talk about traverse, one of the methods of surveying. It is still used in current forms, current system. Traversing is basically a connection of distance or survey lines. It's a series of connected survey lines or distances. Now you are picking the terms as you go along. Any distance measurement that is made reference to for other measurements is called a survey line. So when we talk of a traverse, we say a traverse is a series of, and I think the other time I said it when we were dealing with traversing triangulation, a series of connected lines or survey lines where these connected survey lines, which are distances in themselves, are measured, and the angle between these lines are also measured. So what is the storyline like? I want to take you back to a picture I showed earlier when I was talking about classification of survey by methods. Just a minute. I want to load it. All right. All right. So traversing is any activity in surveying carried out on a series of survey lines. So now you are used to survey lines. You've heard what it means. A distance measurement between stations in a survey that are critical for other measurements as well. So survey lines are connected in sequence, and this is very, very important. One, from here, series of survey lines. First one, connected in sequence. If you miss this one in sequence, your traverse definition is wrong. So you have survey lines connected. Practically, what we are talking about is we are something of this nature. That's what we mean by connected. So one line to another, but you see that they will be forming angles. angle there. There's another angle there. Okay. So when you are dealing with a traverse, you have a series of lines or survey lines, but they are connected, meaning that one ends and another one begins. One ends and another one begins. One ends and another begins. When that one happens, you will see that between any two lines, there are angles. Between any two lines, there are angles. So when you are carrying out a traverse, we will see you to be measuring distances and angles or directions. But the overall design is that there are segments or what we call survey lines, one joined to the other, and you will measure all these survey lines together with the angles between them or direction relating the two. There are two types of traverse we can have: open traverse and closed traverse. Open traverse and closed traverse. Most often in surveying, when a survey work is said to be open, what it means is that you can carry out the work all right, but you have no means of evaluating and checking for errors. Although we know our work will involve errors, there's no way of assessing the error in the work when the survey work is captioned or declared as open. However, if the activity is closed, as in a closed traverse, it means we can assess or determine the error of the work, compare with acceptable error levels, and when we satisfy that, we go ahead to correct. So we have said that traversing is an activity surveying that is carried out on a series of survey lines that are connected. You don't miss those keys. A series of survey lines that are connected in sequence. Or somebody will tell you a series of survey lines that are connected sequentially. Also correct. So you measure the distance and the angles between successive survey lines. From the design, it makes it a traverse because there are a series of lines and they are connected. But there can be various instruments at the center of this activity, which can also give a twist to the type of traversing that you are doing. For instance, I can move along these lines via a distance and direction concept using a compass, meaning that I can set out and move along this line with a compass, turn this direction with a compass, turn this direction with a compass, turn this direction with a compass. Because the compass is the main instrument of the traverse, I can call that activity a compass traverse. And it is one we have wanted to look at how we deal with in terms of plotting, in terms of computations and other things. But I may not necessarily talk about it now. So we'll see where we can fix that. But I'm still giving you an idea about what a traverse is. So we've spoken of the chain, some issues where you are looking at the traverse. So you can have compass traverse, you can have chain traversing, meaning that you're using the chain to do that. Then you can also have plane table, which is an old method. Theodolite, which is also an old method. But the new of these two is what we call total station traverse. So when you are doing total station survey, At times, you can deal or handle a traverse as well. Now, please watch these two diagrams carefully. Richard, your hand is up.
Yes, please, I have a question.
Okay.
Concerning the types of traversing, assuming we see a question that explain 4 types of traversing, and then the last one to the right, we turn it and say total station. Would you accept that one, or we should write the to the right one?
Oh, in fact, for traverse works, usually when I set questions on them, I don't usually use the module that you have described. But in terms of what I've said and how I've opened up the lecture, yes, theodolite traverse is not total station. Set of fundamentals. Why? If you are using the theodolite, you cannot measure distance with the theodolite. So when you do a theodolite traversing, we will see you using the tape because you need to measure distance as well. But when you are doing total station traverse, that instrument can measure distance, it can measure direction and angle. So there will not be the need for any other supporting measurement or two. I don't know if you are getting something. So you see that when it is theodolite traverse, your narrative will include the theodolite for angular measurement, but you need a tape to add to it. That is why if you look at the notes or what I'm displaying with you, look at the theodolite traverse. Traversing by means of chaining for the linear measurement and angular measurement by means of the theodolite. So you will run into a challenge when you are trying to describe the survey. If you write total station traverse is possible. But when you are describing it, there will be no mention of the word chain. So that is where it differs. Now you will describe what is done. I don't know if I've answered your question. So in reality, you cannot use the total station traverse as a substitution for theodolite. Because when it comes to your description of the traverse, you'll be found wanting. The scheme will be expecting you to include the aspect of the chain for distance measurement, because we all know the theodolite cannot measure distance.
Thank you, sir.
Have I responded clearly?
Yes, sir, please. Thank you.
Okay. But I don't tend to ask. If I'll ask you, is direct to whatever, but I may not ask you types of discuss the types of. I may just talk about, let's say, compass traversing. You do this measure, you do this measuring. Is it true or false? Is it correct? Do we what are the issues when it comes to the compass traverse? So usually, specifically, I don't do the generality. But with what you are saying, though you have done total stage traverse, it's not the same as theodolite traverse.
Okay, thank you, sir.
You're welcome. Good. So why do we call a traverse open and why do you call it closed? I said in essence, there are so many survey work you may hear this in association. Leveling is one of them. When you're doing leveling, you can have an open level, you can have a closed leveling. Traverse is another. Okay. So we'll just talk about the open and closed traverse and I'll end the story until such a time when the construction and other things can be taught through. Just trying to see how I manage my time. So take note of that. All right, so when do we say a traverse is open and when do we say a traverse is closed? Let me begin with the second one. When you say a traverse is closed, the understanding is that you started the work from a station with known coordinates and you ended the work on a station also with known coordinates. I'm going over again. A traverse is called a closed traverse if we begin the work from a station of known coordinates. We are now going to do coordinate system. But when we say something is known coordinate, it means it has eastings and northings. It has value that will help us to locate it physically on the ground. So who is a closed traverse? A closed traverse is a traverse that initializes or takes off from a station of known coordinates and ends on a station of known coordinates. What this diagram for me? This is a loop traverse. Why we call it a loop is that it begins from a point, go all around and comes back. The loop is LOOP. But this is a closed traverse because you began from point A with this coordinate. The coordinates are in the box. So you started from point A, you measure distance, you measure distance, you measure angle, you measure angle. And you went round and came back to the A, which is still having a coordinate. So the start was A, the end was A. It's a loop. So this diagram is a clear example of a closed traverse. What makes it closed is that we began with this that had a value, the coordinates. X is 4. Let me blow it up on that side so that you see. 431086 meters. Y is 380,778 meters. Then from here, it went all the way, came down all the way, and then connected back again. So because A is a station with known coordinates, and you started from it and came back to it, you have created a closed traverse. At times, it is not a loop like this. At times, it is a link like this one. So you can start from A with all the values and then go and end on G. If the G that you are ending on has a value, then it makes it closed. If it does not have a coordinate, then your traverse is open. Can somebody recall what I just said in explaining what an open traverse is and a closed traverse is?
Hello, sir.
Yes.
Those drivers,
He said that.
Hey, two people are talking. You didn't raise your hand. My initial was the lady first. So maybe if you wait, let her finish. You see?
The close, they have a coordinate, but the open they don't have.
Wrong. People I talk plenty, but you only pick one and leave some. When you do that, you'll still be writing some and leave some. And that is where you have the challenge. Yes,
You,
maybe I'll
you
come to you
go
by
fast,
wait.
so we cannot write.
Okay, Kunedu, is it
Okay,
Kunedu?
so sir, no, it's me.
Okay,
Okay, so what I understand is that with the open um traverse, it starts with a coordinate, but the end there is no known coordinates.
good. So there's a point you start the work from, which has a coordinate, and you go and land on another one, which has a coordinate, then it's closed. But if you start with a one which has coordinate, but you don't end on one which has coordinate, it's still open. So what makes it closed is that you must start with a point that has coordinates. In survey, we call that control point. So it should be a control point of known attributes. Then you end again on another point that has coordinates. Then you have secured closeness. But when you take off with a point that has coordinates, but you don't land with a point or you don't land on a point with coordinates, the last point that you landed will be treated as a control of unknown attributes, and therefore your traverse is open. So get a connection. Start and end must appear in your explanation. But the difference between the two is that for open, they start on the point of known coordinates, but they don't end on the point of known coordinates. They can still be ending on a point, but the point may not have coordinate information. So it still makes it open. But for the close, you start with a control or a point of no coordinates, and then you land on another point of known coordinates. But when it is a loop, like the first one I showed you, you will go and come back. So it will look as if it's the same point you've gone and come. Yes, but it is correct. It's still correct. The mere fact that is the same point is not the definition. The definition is saying that start from a point of known coordinates and then go and land on a point of known coordinates. Your start and your finish all must be resting or landing on the point whose coordinates are known. Then you have a close. But when you start
So say
on the
if
known
you
and you
land
don't land,
on unknown
it's open.
point. Okay.
I saw, is it Becca? You had your hand earlier on up.
Yes, sir. I wanted you mentioned a name for the known coordinate, the beginning one, but I didn't get it, so I wanted you to mention it again.
Oh, I was just saying
But it
that
seems
in surveying, the
oh,
point with the known coordinate is called a control.
uh-huh.
Control. So in
Thank you.
surveying, when we say control point, they are points who are supposed to have known attributes. But even in the typical survey, we are careful. Because at times you may go and meet a control in the field, but you don't have data covering it, so you don't have information about its coordinates. If you use it for your work, it will still become an unknown coordinate. Unless
Okay,
you have the
thank you.
information about it in terms of the eastings and northings, then you can be confident and you can still call it a control point. So the stations that we occupy to do the work, in certain parallels where they have values like coordinates, we call them controls. So when you are doing traversing, it is expected that you initialize or take off from a control, and then you end also on a control. Here, our understanding of the control is a point with known information on coordinates. If they don't have known information on coordinates, you will run into trouble. It will still become a point, but it's not going to help you in terms of coordinates. So it will still make your work open. So the only time it becomes closed is that you start with a point that has coordinates, what you call control, and then you land or end also on a point that has coordinates, and it's closed. If you don't do that, any other variation is open. Maybe.
Yes, sir. So, sir, please, the traverse with the close one, it can be in a line form. If
Yes,
the yeah, okay,
it can be in a line form, but in that case, the 2 points, the start and
must
finish,
be known.
they all, yes, they all must have coordinates.
Okay.
Mm. So that's the difference between the line and the loop. So when you are dealing with a loop, you can start with the same point, go around and come back, and then you have a loop. So in that case, you are dealing with only one point, the start point. So if you have information, then it's satisfied because in the definition, we talk of start and we talk of finish. So in the loop, the only difference is that when it's the loop, the start and finish are the same point. But you can also have a line. So when it's the line, then now and then definitely the start and finish are not the same points. But for them to be close, there should be points that have coordinates. Are there any questions before I move to the cartography session? I'll be breaking for some 10 minutes. When we come back, we are going to start cartography. Okay, Nora.
Sir, so from our book, the first account of the line, we can see from the explanation you've given, we can say that the top one is a closed service, and then the loop is actually no, the line traverse at the top there is an open traverse, and then the loop is the closed traverse. Am I right?
Thank you. Yes, you are right.
Because looking at the top
Yes.
one, it doesn't have a
Coordinates
known
for
ending
the gene.
coordinate. Yes.
Yeah. So the gene does not have coordinates. So it
Yes,
makes it
the two
open.
doesn't have. Okay.
Yeah. Suleiman.
Thank you.
Okay. So if there are no other questions, it's 2:31. We are breaking. 10 minutes from now, 2:41, we are starting cartography. Thank you very much. You're all welcome back.
Thank you.
Thank you, sir.
We want to look at cartography. We dealt with surveying, and then you are going to look at cartography. In fact, like I said, some of the issues, they overlap here and there. An example is map reading. An example is a coordinate system. I'll touch on them briefly when I'm doing the cartography. But surveying also can deal with them. Sometimes, depending on who you are reading your distance from, both ways are consistent with what they mean. And they are used as such. Cartography is defined as a discipline dealing with the conceptualization, production, dissemination, and study of maps. Other definitions much simpler. Look at cartography as the science and practice. The science and practice of map making. In fact, I've seen other domains where they put it as the study and practice of map making. They are all correct. But usually I like this one that I currently shared with you. And with modern technology and instruments, the art and science to allow that one. Initially, when they began the subject matter, computers have not evolved, and we don't have it as now it is in passing. So somewhere along the line, the discipline had to force and move from analog cartography to digital cartography. But still was the domain where we make maps. So whether you are the one that use the study and practice of map making, you are the one that talks about the art, science, and practice of map making. Correct. So it's also what is on the board currently, or I'm sharing with you currently. So like I said, you could have analog cartography belonging to the old block, and you can have digital cartography with the use of computers, how we make maps. In terms of even the work and practice, we have those who deal with thematic cartography, and there are also those who deal with general purpose cartography. But this becomes more of a categorization of cartography when we look at how they handle maps and produce the maps. Because that idea of thematic and general cartography is coming from the use of maps, which may be categorized, as we have seen earlier, as thematic or general reference. You recall. When we talk about history of map making, we added that. So we said in terms of types of maps, we have the general purpose map and then we have the thematic. So when you try to produce a lot of the thematic maps, it is also ascribed to you as a speciality. So you can say you are dealing with what called thematic cartography. You are making maps, but you tend to focus on one or two things at the time. There are elements of cartography that we need to look at. The elements as may be suggested or drawn from the definition covers about 4 areas. Because eventually you end up making maps, issues of cartography are dominantly issues of the map. And by that, what we mean is you can have scale issues to look at. We have to consider map projection issues, which may incorporate into it map generalization. We have to look at map design issues. Where do we put what? And what are the things that can represent things about our real life? They are done
Hello,
in
sir.
map design. Yes.
Hello, sir.
You continue to say hello, sir, and I respond. Is it that you are not hearing and you want to justify your this thing? Or when I'm talking, you don't hear? Which?
Yes, sir. We can hear you well. Your voice keep on
You can't hear
coming
words.
down and coming up. Yes.
Okay. Let's see. Technology. Is it any better now? You hear me well now?
Yes, sir. Yes.
No, I'm talking about those who were making the complaint. At times it's the network at their end, but they are unable to tell. So when they raise the questions and I try fixing things, I want them to respond so that we'll know that really it was coming from my end. Well, if they don't respond and you on the other side who didn't ask a question are responding, it makes it difficult to assess whether not network affecting them there. And they are other thinking's mind. All right. So we have this element that we need to look at generally when it comes to cartography, because your main output when it's cartography is your map. Any cartographer, everything you do ends up with a map. So all that it takes and all issues related to the map to get it well done are expressed in these issues: skills, map projection, map design, and then map construction and production. So these are the 4 things, the issues. Their explanations will come later, because I believe you can read and get it well. For instance, we've discussed map scale already, isn't it?
Yes, sir.
So how many
Yes, sir.
representations? How many representations of the map scale do we have?
Sir, please, you have 3.
We have 3.
Okay. So we have the linear scale or graphic scale, number one. We have the verbal or statement or word scale, number two. Then we have the representative fraction or fractional scale, number three. So these issues are important for the cartographer. Why? In the first place, like we saw in the earlier discussion, and we may also see when it comes to map projection, is that whatever that we are representing, whatever the surveyor measures and the cartographer tries to represent, are things that are on the Earth surface, number one. And two, the Earth as a surface for representation is far, far bigger than our space that we use for representing maps. For instance, no map has been able to measure and plot features on the surface of the Earth at a scale of 1:1. Because 1:1 will mean the same size. But here we are, we take A4 sheets, we take A3 sheets, and we try to map and show maps. So we are not able to match to reality. We are always dealing with a reduced form of the reality. That is fine. But it also means that we need to understand how these reductions are managed by the scale. So what scale you use is very important. In the first place, we are admitted, whatever that we show as a map, they are reduced form of the reality. Fine. But then, depending on the scale you choose, some of the reduced form of reality will appear okay and appreciable. The same feature at another form of scale, it will be a dot. So scale matters. Two, projection. Look at the globe. The globe, as we know, if they show it to us in class, is being spun around. In that globe, there's Ghana. In that globe, there's Nigeria. In that globe, there's America. In that globe, there's Italy. In that globe, there's Russia, Japan, all of them. So whatever that we see and whatever that we discuss is a reduced form of the issue. The reduced form of the issue. How do we deal with a reduction? And how do we also deal, secondly, with information we've captured from the surface of the Earth? Curve, geodetic versus plane. I'm not looking at measurements, I'm looking at transfer surface. So how do we deal with information that is on the surface of the globe with the curve characteristics? And you depict it and show it on a flat surface like a sheet, A4 sheet, A2 sheet, A3 sheet. You need to appreciate projections. It is why, one of the reasons why surveying and for that matter cartography, at times people don't like it, because there's some element of mathematics that comes in. So we have the ideology, fine, but to help us carry out the ideology, we need some mathematics and science to deal with that. So we produce maps and we produce them on flat surfaces, but we pick data from the Earth and around the Earth from a curved perspective. So the subject matter that handles this properly is called map projection, where we look at how we gather information around us from a curved surface perspective with flat surface presentation. So that is it. Then we need to look at generalization. Generalization in the sense that our ability to show everything is limited by the space we have, number one. Our ability to show everything is also linked to scale, number two. So there is what we call limitation of maps, and note it down and go and find what it is about. When we say the limitations of maps, what is it? Benefits or importance of maps. If I didn't give that to you, note that one too down. Sorry for nothing at all. Today I'm talking about 3 assignments. We've spoken about the earlier one on the errors in chaining or taping. This one, I don't know. I may have given it to you earlier, but I'm not sure. If I have, I'm just re-echoing. If I have not, you have to note it down. The importance of maps. And the last one, we are looking at the limitations of maps. So what I'm saying is that because we don't have a large surface to depict or show things, we are at times limited in how big the thing looks like and how we want to represent it. Then, as we have discussed in the first point, scale. Scale is linked with how much space we can show. So, in order to manage things and still reduce things within a limited space, at times we have to be able to bring in cartographic generalization. And what does cartographic generalization involve? It's the same as generalization when you hear it generally under map and cartography, the same thing. Cartographic generalization is looking at representations in the map, and at times changes are necessary when we attempt to reduce maps because of the type of scale and output we want to display. Generalization again is important because it's not everything you capture that you can easily put inside a map. So in generalization, you tend to place emphasis on what is more important and must be seen, even to the detriment of others that may have been captured or recorded in the field. So anytime you hear of the cartographer and map making, generalization is the next key thing. What I have gathered, which one is important, which one do I put in, which one do I have to hold on? So all of these are the kind of challenges the cartographer goes in because he wants to be able to manage the content. So you have to end up generalizing. So why do they have to generalize? You want to avoid crowdiness. Two, you want to improve on the visibility of objects that would become too small. Three, you want to better visualize the symbols and representations that you put in the map. Let me give you an example, which is very, very key. Number one, road networks that connect communities. They have a width and they have a length. But as far as they are concerned, they are typically key features you cannot leave out in a general map. No matter the scale of your map, if the road network has to show, because you want to get access from one community to the other, you use generalization, you will still show where the road is lying. But maybe according to scale, that is not possible. As your scale becomes small scale, the features will become small. For instance, if I'm drawing a map of an area and I started it 1 in 1,000 as my map scale, it is different when the same area I go for 1 in 100,000. Things will begin to look small, and in some cases, the form of the thing may not even appear. Yet, you want to show significance for it. You want to indicate it that it's there. You will find a point feature to still represent it. When under the scale, it's not supposed to show, or it will be very small. So generalization will tell you, because that element is key, for the sake of that map produced, you use generalization so that it can still show the road. So when I put a symbol like, for instance, our Kotoka International Airport of Ghana, it's a spread out, it's an area concept. Depending on the scale of the map, it can shrink to a point. Depending again on the scale of the map, you cannot plot it. But I want to still show that there's an airport in Ghana which is of international standard. So in the end, I'll pick a point location, use a symbol like an aircraft or an aeroplane, and tell you that that's an airport. So that's generalization, because according to the scale, it will not be impossible to see. But by importance, you have still showed a symbol and you're saying it's Kotoka International Airport. So these are some of the reasons why we want to do or go into generalization for the purposes of map. Another major area when it comes to cartography is map design. So after the general, I'll start talking about certain topics. That some fit into map production, that some fit into scale. Out of scale, I've done it in the earlier sense. So what I would have done here typically is the construction of scales. So that's when we visit it again. So when you are doing a map, you need to put in a scale. Yes. Hello?
Hello.
Somebody was raising some things. I saw some hands dropping. I don't know if they were mistaking you or. Okay. So every cartographer must understand map design. Map design is where you bring all your skills. Skills about how to use symbols properly, know the nature of the symbol and its size, know the form of the symbols you are using, even the type of lettering. When you write that this is Accra, what kind of font do you adapt? What kind of font size? Specify the weight of lines, selection of colors. All of this constitute a special aspect in cartography called map design. And we'll look at some of the issues related to that. So you always have to go through some kind of planning in the end. Because if you don't, at times they are what we call conventional sign symbols. I don't know if you've heard of that before. What
Yes,
are
sir.
usually
Yes.
the representation that we give to water? I'm yet. to see somebody who has drawn a nice map, and then he has a pond or a river, and in the legend, the pond or river is indicated with a red color. But that shouldn't have posed a problem. Why? Because I am doing the map, and when I did it, I explained to you. I said the red oval thing that you are seeing is a pond. Yet you see that there are some challenges you have with trying to read that map or appreciate that map, because the cartographer decided to go against what we call the conventional sign symbols. If he had, he wouldn't give red as a color for water. But what we usually expect is a blue color. So map design is very, very critical. And the last aspect, putting all the pieces together, constructing and production. Construction, production. This somehow links with the kind of history of maps that we did. But here we are talking about generally two areas: the old times and the new era. When we were in the old times, called classical cartography, we typically were dealing with map construction and production using pens and inks, and to some level, some printed mechanical machines. In modern era, however, our map construction and production has taken a different twist with the advent of computers. So everything is now being run through the computer, even to automation and printing to the computer. It makes life simple. It makes life easy. We are able to print more maps, even if the supply is meant for a large audience. For instance, if a school contacts a mapping house or a map production house for a particular number of copies of a map to be printed, because they want their students to make use of it in their map reading interpretation, in their surveying and cartography. So you can imagine the old era when we didn't have computers and we couldn't print at that fast rate. When your numbers are running into 100, 200, how would that cartographer, the center of it, be able to handle such numbers and still be able to produce? So clearly, the map construction and production aspect enables us to see what has happened in the past and what is happening now, purely by the difference in application of computers and technology.
Madam Elizabeth, mute your microphone.
So that is the aspect. When you are going to produce, back then we use a lithograph and all kinds of techniques, fill codes and the like. Modern era computer. So once you have your computer, one or two softwares, you know how to learn and manipulate. You, the cartographer, just bring your information on board, and then bingo, next time you are printing. So we have talked of maps already, and yet we see it. So what I'm going to do quickly is to look at some of the topics relating to this, which are essential for us, like the coordinate system, because I've dealt with maps and the definition of maps earlier. This also talking about the maps, but it goes further to look at the content of the map. I'll come back to this issue again. But then I want to pause here and look at the coordinate system, which is used for representation of geographic phenomenon in the map environment. Hello?
Yes, sir.
All right. So let's look at the coordinate system. The coordinate system, typically, what is it? The coordinate system.
Hello.
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 Yes.
Oh, okay. I wasn't hearing from you, so I thought it was a problem.
I'm trying to load the document and it's not working. All right. Let me do some check. I'm going out. I'll come in and see what is happening. Start. So just give us 5 minutes. I'll get back.
Okay, dog.
Network in Ghana. Oh, mama, yeah.
Madam Abigail, please mute yourself.
Somebody's hand is up. Oh, maybe he want to explain the coordinate system. So
Hello, Sister Constance. Do you want to take over as TA? Your hand is up for
the
long.
hand is up. So yeah, by now, crowd the arm will be penny here.
So, John, please pay attention well, okay? You understand?
I know they see tough. Oh. It shall be well. Yeah, we are managing. It shall be well, Papa.
Yeah. Professor Sempa, can you please take over?
You think this is for children's play?
Hello.
Hi.
Good. So we want to look at the coordinate system. Basically, when you take a map of any sort that you are using, there are mapping units of the map, and there's a coordinate system also embedded in the background of the map. The other time, I think we talk about maps. I don't know, did we speak about the characteristics of a good map? Hello.
No, Mama.
No, sir. No, sir.
No, please.
All right. So when you have the cartographer deals with maps, as we're seeing the last thing, there are certain major things you have to put on the map, like the title of the map is very, very important. You have to do that. Like the scale of the map, the orientation of the map, the north arrow direction. Somehow the copyright or bibliographic information that tells us the year of the map and all of that. The legend. So there are some basic things. When it comes to the map area, what he puts there is called grid line. And the grid lines have values. Depending on the values assigned, it will belong to one of the two possible coordinate systems that we talk about. A coordinate system is basically a locational reference system. For us, the simple way to remember what they stand for is to go for our graph book and then pull out our graph sheet and then begin to understand certain principles like the X and Y axis. You recall?
Yes, sir.
And once we step into that, we are talking about a coordinate system. The fundamental reason why we have to go through a coordinate system we determine the position of a feature on the Earth surface. When we come to the classroom, how are you able to tell if the position where we sit are supposed to be permanent locations with our name embossed on them? How can we tell the position of Sheila from probably the position of Emmanuel or Elizabeth from probably the position of Mavis? We have to define a system that helps us to do that correctly. What about the next one? How do we measure distance and dimensions and movement of spatial features? Today I am in Ghana. Tomorrow, because of a conference, I go and seek visa and I've traveled to the US. Spatially, is Ghana at the same location as the US? No. So how do we consistently get it right? So that when I give a definition of a location, somebody can trace it and say, this is talking about Ghana. And not use the information and go and end up at the US. How do we determine height of any given location? Very important. How do you determine the motion of features on the Earth surface? So if I tie a detector to your leg, today you are in Ghana, the next day, because of a conference, you have moved, you are in the UK. The detector will tell me that your position is not the same. You were then here, now you are here. Movement. All of these problems are fixed when you have an understanding of coordinate system. It goes through a process we call georeferencing, but for now, don't worry your head about it. But they are very, very important for us. So we say all elements in a map have specific geographic locations and a sense that enables them to be located on or near the Earth's surface. Our ability to accurately locate geographic location is crucial in mapping and in GIS. For that matter, surveying and cartography, because the mapping aspect has to do with surveying, cartography. So generally, we tend not to, as it were, be mindful of the role of the cartographer, but it's very critical. If you map all the information and the cartographer cannot put it on paper in the form of a map, it's useless. So to be able to describe locations and shape of features requires a spatial reference framework for defining real-world locations. So we come to our coordinate system. It's a reference system used to locate the locations of geographic features. So in a brief, it is a locational reference frame. The locational reference frame. In any coordinate system, there are about 4 key areas that we look at. One of them is what we call the measurement framework. Where are we relating our measurements? Is it over the globe concept of curved surface, or is it over a flat concept of projected surface? When we are with the curved surface, one of the 2 types of coordinate system will be more suitable and preferred, the geographic coordinate system. In the geographic coordinate system, we use longitudes and latitudes, so they support curved surfaces appropriately. In the projected system, however, is more suitable for flat surface. This means that in the cartographer's mind, if your map is going to end up printed on a flat surface, and the cartographer would have preferred the projected coordinate system rather than the geographic. Because it is with the geographic that you have longitude and latitude representing curved surfaces. With the projected used for civil and other work, we want the flat surface. Hello. So when you are looking at the measurement framework, then there are two forms of coordinate systems we can use. Geographic, where we use longitude and latitude, and projected, where you use axis of eastings and northings in surveying, or generally what we call X and Y. So when you're having the X and Y as in the use of a graph sheet, you are looking at a flat surface. In fact, there have been times and there are moments in 1 in 3,000 topo sheets where all the two systems have been implemented. But the only way you can tell the difference is tracing out the grid lines and their various values. If you find a grid line, yes.
Hello, Doc.
Yes.
It looks like your voice is far away from the earpiece you are using, so your voice is very faint in our ears.
Wow.
Maybe it's at your end.
That's what I'm saying. But this is usually
Good. It's from his end.
Not his friend, his end. It may be from doctor's place. The voice is far away from the microphone. It's true.
His voice is far away from the microphone. I've connected it to my speakers, but still.
All right. Let's see. Technology. So, as I was
This
saying,
course is not good for online.
in terms of the measurement framework, there are two types. Or generally, in terms of coordinate system, there are two types. Geographic coordinate system that uses longitudes and latitudes, and projected coordinate system that is more preferable for a 2D flat surface measurement. When you are with a geographic using longitudes and latitudes, your measurements are in angles, they are angular. So any geographic system that you load or work with knows that it supports angular measurements. This is not the case with planimetric or projected. In projected coordinates, we deal with either meters or feet as our reference. So that is clearly in terms of measuring units between the two systems. Then we can also look at map projection. Anytime you talk of a coordinate system, you must understand the role of map projection. Map projection is a systematic transfer of information from a 3D globe with a curved surface onto a 2D flat surface. So anybody who handles map projection, coordinate system knows that there are two forms. And to be able to move from the geographic to the projected and vice versa, you need an understanding of map projection. We may consider other issues, like in the projection. What is the spheroid of reference that we want to use? Which one is better suited for our area than others? For instance, Ghana uses a model we call War of It. War of It is a geographic coordinate system for Ghana, designed by the British Army because they colonized us earlier. But then there are other spheres like WGS84, which works with the GPS system that is applied worldwide. So in all of these two systems, whether War Office or the WGS84, measurements and locations are defined by longitudes and latitudes and height systems. It may include a datum, and I'll talk briefly about datum. Projection parameters like the standard para, a central meridian, possible shifts in the X and Y. All of these things, it comes up when you are dealing with map projection. So I may not spend so much time on them here. But when you are dealing with map projection, the central para or central meridian will become important. What's the difference between a central meridian and a standard meridian? You have to be able to explain that. So briefly, we've seen what the two systems are about, what they stand for. So in terms of the characteristics, we've mentioned about 4. And in terms of the types, there are 2. Global or spherical coordinates, or what we call geographic coordinate system. And then we also have the projected. The rest, we can read about them and have an understanding, because longitudes and latitudes, this is not the first time I've been hearing them. And when we read their properties, they are also self-explanatory. So we have the geographic coordinate system, suitable for curved surface, uses longitude and latitudes. Measurements are done in degrees and by extension, minutes and seconds. So you can have degrees only, you can have degree minutes, you can have degree minutes and seconds. They are all possible under coordinate systems. For specific location and map projection issues, we may have to include meridian, which is prime for our projection, and a datum or a surface considered and deemed accurate under mathematical modeling and processing. The rest from here on is about the longitude and latitudes and their characteristics. So that one I'll leave it as a reading material for us. So to the left, we see here are the latitudes. They run from the east to the west around the Earth. Then we have the longitudes that run from the north to the south over the surface of the Earth. When these two combine, then we have location defined the geographic, and the network they produce is called a graticular network. Graticular network, a network of lines of longitudes and latitudes intersecting. And there is more of a graphical representation of that. And the added information here is that latitudes are known as parallels, because if you look at the orientation and design, every latitude is parallel to the next, either above or below. Longitudes are also known as meridians. So when you talk about the 3 meridians surveying, it's because we are looking at an alignment that is towards the north. So the rest, like I said, is carrying the characteristics, and you can read through them and have it. It brings us to an important subject we began. I told you we may meet it again, and here we are with it. How do we define location? How do we define location in this medium? Ima, you have your hand up.
Yes. My question borders on the sphere you shown earlier. From the beginning of this, that the Earth is not a perfect sphere. So my question is, why then do we still keep the model of the Earth in the spherical form, and the maps that we are constructing and all references, we still have that in reference to this perfect sphere? That's my question. And a reminder, I think you promised us from the first lecture that you will bring a National Geographic information on the real nature of the Earth, and then you also show us the solid Earth, as in the land mass without water. So I'm just reminding you of that as well. Thank you.
Thank you. Yes, we still keep going to that because that is a simple general representation of the issue. So in surveying, just like you saw under geodetic versus plane, plane is saying that assume that the surface of the earth is flat. That may work only when you are considering a local area, not too big. But if you are doing a very big area, then the curveness cannot just be ignored. So even for surveyors who have to learn and deal with accuracy and measurement being accurate, they still make use of some of these models as a start-off point. But they admit that you cannot use this for precise measurement. So you start from this because when you're looking at the curved surface, what model can you use other than the simple globe? And our understanding of longitude and latitude is that longitude moves from the north to the south pole and they have a curved surface. So if you're talking about a curved surface, the only way to represent a curved surface is a curved line. That will give you a smooth surface. But of course, what I said about the real nature of the earth is so, and thank you for reminding me. I'm sure I will put the document and then run it and then use. So that is it. So we still make use of them because it's a simple form of the earth. And from that, we can move out to a more accurate one. If only we can handle the mathematics and then the issues there. Thank you about that. So we continue. So we have longitude and latitude representing location. How do we do that? A location is typically defined as the intersection, as you can see from here, the intersection of a longitude and a latitude. When you're in the projected, your location is the same. An XY or an X axis coordinate intersects with a Y axis coordinate to determine location. If it is 3D, then a Z component will appear. So what we have here is an example of Cape 3 Point in Ghana. And the latitude position of that one is 4 degrees 40 minutes. And the longitude closest to that point is 2 degrees 5 minutes 28 seconds. 2 degrees 5 minutes 28 seconds. So this is one style of defining the longitude and latitude. We call it degree minute seconds. There's another form called degree decimals, as you are seeing down here. And this is what usually when you are solving mathematics and other things that involves angles, we tend to use a whole number and decimals of the whole number, all with a degree. So usually here, you will see a small knot at the edge here for a degree. So it is 4 degrees and then 0.66667 of a degree, which from our understanding here will contain both the minute and the second. So how do we get them? For social studies and for us, that headache is not fast. But if you are doing GIS and you are doing a BSc program, you have to go through that. So for now, I'll spare you the difficulty of computing. A lot of you already are afraid of your mathematics. Good. So what's the idea? Anytime we want to define a location, if it's geographic, we want the longitude and the latitude that are crossing the feature. All right. So we proceed. The rest, like I said, are attributes of the equator. Sorry, of the longitude and latitude. And you have to read them and get every one of them clear. Can easily be asked them. For example, we know that it is all longitudes are great circle. And when we say something is a great circle, it means it splits the earth into two equal halves. But in terms of the latitude, it is only the equator that splits the earth into two equal parts, and therefore a great circle. So the latitude is only the equator which is a great circle. But for the longitudes, each one of them represents a great circle. So I'll just touch on a few, the rest is really different. Projected, I said it earlier, for flat surface representation, such as when you open your computer and you pull a map and you are showing it, it's on a flat screen. When you get a map onto a paper, it's on a flat surface. A projected system, we have axes. If the axis involved is only X and Y, it's a 2D representation. If the axis involved is X, Y, and Z, it is a 3D representation. In a projected system where the axes are meeting at 90, we have what we call a Cartesian representation. Cartesian representation. What are the types of maps or types of projected coordinate systems? We have the Mercator projection as an example. You may have heard of UTM or Universal Transverse Mercator. Then we have the Transverse Mercator, which Ghana uses, and other forms for the US and Canada, for instance, which is the Lambert-Koenig conformal projection. These issues come up again when you look at map projection. But here, we are mentioning them as examples based upon the surfaces they apply them for. And all in this list are for projected coordinate system. I'm giving you a fourth assignment. A fourth assignment. Write them down. WGS 84. War Office of Ghana. The last one. Is for you to determine.
This is the second one I didn't hear.
W.
Sir, please.
The first one.
Can you start again for us because the network was against us?
WGS 84. WGS 84. Let me duplicate this slide and write it so that you see. This one is used by Ghana. This one is used by GPS for worldwide application. This one is only used for Ghana. The wall of it is for Ghana. The WGS84 is for most global applications like GPS systems. Then the last one is find out what is the reference spheroid for Togo. Did you see that? Are you seeing now?
Yes, dog.
Yes, sir. Yes, sir.
Dog.
So write them down quickly and find information about them briefly. It is important for you to do that because we will talk very soon about datums and they will come up there again. But here I'm looking at it from the geographic coordinate system perspective. So they are added examples and their names is what I've written. WGS 1984, some call it WGS 84, the same language. The same language. So the first two, all that you have to do is to read about it briefly, what it stands for. And then what this one, but this is used by Ghana. The second one is used by Ghana. The first one is used for most accurate measurements across the world. And the last one, you have to find out and tell me what is the name of the spheroid that they use as their reference. Good. So we move from coordinate system to map projection.
Doc, please, are we meeting Tuesday and Thursday again?
Come again.
Please, are we meeting Tuesday and Thursday next week?
No. In the beginning, I said if we need to meet, it may be on Thursday.
Oh, okay. Thank you.
Thursday at 6. It's likely we'll meet, but not Tuesday. It's likely we'll meet on Thursday, but it's at 6 o'clock.
Okay. Thank you so much.
Yeah, 6 in the evening. And by 8 or maybe 8:30, we are done. All right. Good. So what is map projection? I'll start briefly, and when I finish, the rest, I hope you have been jotting down. How many assignments have I given to you?
Sir, please, the first one you give us one, and then this very one you said we should go and find out. You said you give us a question on bearing, and that is yet to come.
But I've
So you have given us
mentioned,
about three assignments.
I've mentioned about 3 or 4 already.
Yeah, sir, you said errors in training.
Thank you.
Then
And what again?
importance of map.
That is no word yet, but I did mention that. Importance of map, when you go and check on online, you will get that one. It's not even under 10 minutes, you get all. Importance of map, limitations of map.
Sir, please. The first assignment when you were starting, most of us were struggling to be on the platform because of the network, so we didn't get it. Please,
Yeah, you're right
if you
to help
can
me. I will not. Just like our sister is doing through the reps, you will get it. So don't worry. So I gave you about 4.
Please mention the rest. Too. Those who had it from the.
Come again.
I was saying that those who had it should mention it.
Some were not real, this thing, but I still said it's important for you to note what is there. I think besides the errors in chaining or taping, we spoke about the limitations of maps. We spoke about the importance of maps. Then we came to the bearing one, which I've not given to you. But then I also did mention earlier that I spoke to you about that's something to do with I'll check my list and get back. But the errors in chaining was one. Then we have the limitations of maps, importance of maps, and then somebody asked something which I've explained. The one we just did. No, that one makes it 5. But there was something I mentioned. So that one makes it 5.
So you mentioned benefits of.
Come again.
What?
Benefits. I have benefits also of
What?
map.
We can hear you.
I had
Benefit of
limitations.
map. That is the importance.
No, I've mentioned that already.
Okay.
We have the importance of maps. We have the limitations of maps. We have the errors in chaining. Then there was another one I mentioned before we came to. Because that one is cartography or something. Yes.
Sir, please, that one is bearing, but you said you give it to us after the lesson.
No, sir, I wrote the role of the cartographer as number 4. I don't know if that's it.
Yeah. It's not part of it.
Okay. So I think when I started the cartography and I was talking about the scale, map reduction, and all of that, I was trying to push for something like that. But you don't worry. So let's have it this way. We have the errors in chaining or errors in taping. Then I told you to look at limitations of maps, benefits of maps. Then I also spoke of the cartographer, but that one I'll redefine it. There are certain things in generalization you are going to have to look at. And when you go looking at them, it comes with diagram and explanation. You have to get all of them right. I may only
About
give
what?
you
About the cartography.
No, it's not the real thing. It's not the real thing. But it's the work that they do. He said they were in 4 major areas. And I said map scale is important. We've done the map skills. Then I spoke of the generalization, map projection versus generalization. And I said That is also crucial. We'll be talking briefly about them and there will be some assignment there. Then we came to the coordinate system and what I've just mentioned. Like what I'm saying, this reference areas for Togo, if you Google car within the next 5 minutes, you'll get it. It's not something that, so I'm not seeing them as typical assignment, but I believe the knowledge you have to get because I may ask you a question there. So that was how.
You asked us question where.
Right.
Okay, we'll go on. All right. So we want to look at map projection.
Yeah, I'm sick. Oh, this morning I have to take my drug and eat. I didn't. I'm not able to take my drug.
Lizzie, go and take your drugs, okay? Later, you come and play the recorded version.
Hey, Vic.
Receiving time.
All right, so let me do my introduction. Map projection, what is it about? The diagram here is simply depicting what happens when we are talking about map projection. I'm pulling this one down because you have noticed the details already. So I should think we are good to go, isn't it? So let me share with you the map projection. So under coordinate system, we saw that there are two forms of referencing: geographic versus projected. But for the cartographer, the ability to pick information from the geographic curved surface environment and represent it on a flat is map projection issues. This you can do a simple experiment at home. Buy a nice big orange, and then cut it into two so that you get a hemisphere, two hemispheres. Scoop the food in there and eat, including the juice and fiber. When you finish, you have a bowl. Now, on the skin, the peel side of the orange, having cut them into two and scooped all the juice and juice sacks and everything from inside, you'll be left with only the peel. Forming a bowl. On the peel side, the outside part, not the inner white one, no, the outside part. Use of sketches that shows representation on the peel using a marker or something. When you are done and after leaving it for a while, now attempt to make that bowl or hemisphere to become flat. The flatness should be against the inside so that the peel will be facing you, the individual. So the flatness is supposed to be attached or become flat onto the table. Then it's rather the peel side that will be showing your face. The green part of the orange that will be towards your eyes. But the inner part will be over the table. Try and make that hemisphere flat as much as you can. You will see that there are some challenges, but try and make it flat. Before you attempt the flat, the bowl.
So sir, you not peel it.
Come again.
You won't peel the orange.
No, I said you will buy the orange and cut into two. The knife.
And I'm saying that you will not peel the outside, the green one. You won't peel it.
No, you won't peel it. The green one is acting as the surface of the earth. when you are considering the globe. So it is upon the green that you use the marker to construct figures or something across the surface. Then when you finish, you turn the bow upside down so that the curved part of the surface in green will face you. And then the inner part that is white will be over the table. And try to make it flat. When you succeed, use a pencil to capture the outline after you've made it flat. And compare with what was happening when it was in the form of a bow. And then give me feedback.
So won't it tear?
Well, that is up part of the exercise. I don't
Part
know,
of
it
the
depends on
experiment.
person to person. Yes, part of the experiment. But it indicates the
Okay.
difficulty. It indicates the difficulty that the cartographer has to go through and the surveyor in trying to use map projection. So that things that is mapped from the surface, curved surface of the earth, they will show it as flat. To do that, our friend, the nature of the earth, we have adapted 3 developable surfaces. One is called cone, one is called cylinder, and the last one is called a plane. Cone. You remember the Christmas hat that we used to buy for our cakes, the one they make with paper? You see when they are wearing it over their head, you see the nature of the cone.
Yes, sir.
Good. And we all have, or we've seen cylinders that we fill for use in the house.
Yes, sir. Yes, sir.
Cylinder has 2 pushers. You can place it vertically when you are using it, or you can let it roll on its side, true or false?
Yes.
True.
Good. Each way, there's a reason why we will take one of the models as against the other. So the cylinder is a developable surface. The cone is one. The last one is a sheet of paper, plain, or like a cardboard, plain, flat, or like a plywood. When you cut and you hold a plywood in your hand, that's what you are calling the plane. Each of these, when we use them for map projection, it leads to different outcomes. When you use the cone, you get what we call conical projection or conic projection. When you use a cylinder, you get what we call a cylindrical projection. And then when you use a flat surface, you get an azimuthal or planar projection. Our Earth is not a developable surface. Now, go and check on this. It's another assignment. Why are we calling this 3 developable surfaces? They are here. If you look at the slide. Cone, cylinder, plane. I think that. Cone, cylinder, plane. Are we seeing the highlight?
Yes, sir. Yes, sir.
And look at the word that was used before they were listed. Developable surface. So my question is, the Earth is said to be a non-developable surface. Yet in map projection, we use cones, cylinder, and planes as developable surface. Why is an object considered a developable surface in map projection? Why is an object such as cone, cylinder and planes considered developable surfaces in map projection, but not the shape of the earth, or but not the earth. Here the earth is capital EARTH. Is it clear?
Sir, please come again.
Hello, sir.
Why,
Sir, please, can you come again with a question?
I said in map projection, why are the cone cylinder, why are the objects cone, cylinder, and plane known as developable surfaces, but the earth as an object is a non-developable surface or non-developable object?
so you said but the earth.
Yes, but the earth as an object is considered a non-developable object or surface. So all of the assignments I've given you, do them all. I've not given you any dates for submission, but do them.
Yes, sir.
Okay, so now let me run the objects that Ima was asking about. If there are no questions, me, I'm done for the day. Thursday, we'll meet and finish off what is left.
Sir, please, let's do it on Thursday.
Do which one on Thursday?
The object one.
The video one I'm going to play.
Yes, please.
Are you? All right. So when we come in, the rest remind me to run that one first.
Yes, Doc. Thank you so much.
Yes, Doc.
First action on Thursday evening.
Thank
So
you,
thank
sir.
you very much. And then
Thank you so much. We are grateful.
the rest, please.
Yes. Thank you, sir.
I
Sir,
hope
sir, you promised
you
to give
send
us
us
the
the
slides, oh,
slide.
but we have not heard from you.
You hear from me. And say, do your notes. Who better notes?
We have done enough. So the slides to help, please. We beg you.
Please, Doc, we have our notes, but we still need the slides.
Sir, please. We need the slides.
The rest. Are you all now on the page?
Yes, Doc.
No, Doc.
Yes, Doc.
Okay. So
Which page, Doc?
rest, are you all now on the page? Who belongs to which page? Okay. Those
Please,
who
which
are saying,
please?
those who are saying yes, those who are saying yes, make sure your friends are on it. If they are not, contact them and collect whatever information. Then that same people, I'm talking to a champon. Sheila, there you are there.
Yes, please, I'm there.
And those who know of it. So if you know a rep is saying they don't know what I'm talking about, talk to the reps and draw them on if they are not there. Then I just need a high. This evening I'm going to start loading some of the information there. And I will be putting notes and other issues to it. Because like I said, make your notes. I'll bring information. Some are slides, some are materials. You are supposed to combine all and know where all fits. And then who you notes now, you will see where they fit. One you notes now. Having a big that And then it does now. We were no, but in the end, the baby now, I can't now answer. We are not already out. One year now, we'll change. When are you writing
Auntie
exam?
Sheila.
Yes.
When are you writing your piece?
Auntie Sheila, could you please send me your number
Madam
so that?
Elizabeth and Mabel, kindly
Please, what
Yes.
is
let her
happening?
finish.
Don't
Let's finish talking. You are all talking.
When
Please,
are you
I am
writing
not
your piece?
talking. I am
Doc,
not
please,
talking.
2 weeks time. Next
Your
week time,
quiz is
I'll
Sheila.
Doc, please, in 2 weeks time.
In 2 weeks
Okay.
time.
Doc,
Next week is revision, right?
yes.
Sir, it's 16.
Thank
Next
you.
week is for practicals.
Doc, please,
But
I was
what practical do you do?
We
Oh,
are
you're
not
talking
doing.
yeah. Oh, you're talking
We are
about
not
those
doing
two courses.
practicals.
Ah, okay.
people do practicals.
Okay.
Doc, please, I was able to get the rest of the books. Thank you so much.
Sorry, Mr. But sorry, I was in a panel this thing for some defense. So,
Yes, please. He brought them to me yesterday. I'm grateful. Yeah,
okay.
thank you.
I'm also grateful that you had the patience and had to always.
Yes.
So please, some of us have we've not gotten some of the books. So.
It's a problem out of power. All right. So thank you very much, and the rest.
All right, thank you.
We'll talk on the other.
Hello,
side.
sir.
Yes.
Sir, please, what about the recorded? What?
Recording the rest, I think you are supposed to contact you. Code, I think. That's
The
how they
recorded
do it.
version, the recorded this thing I always put on the YouTube channel.
And the way it's done is difficult to retrieve the record version. It's so many. You can't even search.
No, just use the code of this program. Just type the code when you go to YouTube. The cartography and surveying will appear.
Those of you who have been doing this and help them to see. Yeah, I'm not trying to do that. So I don't know.
Just when you go to YouTube, just type the title of this course on the page, YouTube page. Only cartography will appear. Then you just click on which one you want.
Okay. Okay. Thank you so much.
Please, Madam Sheila, are you an administrator at the web page?
Auntie Sheila.
No, please, but I have the administrator. Yes.
Okay, then please forward it to me so that I can contact you.
Let me put in the chat.
Okay.
Bye.
Okay, please you put it so that I can contact him to add me.
Sure.
Hello.
Yes, I'm doing it.
Sheila, okay.
Yes.
Auntie Sheila, can you add us to the page? What page is that?
It's for the course rep. So if you are a course rep, then they can put you there. It's for the course rep.
We have only one person, the administrator there. So I'll call him. Then when you call me, I'll give your number to him. Then you add it to your page. Okay.
Then he will add me to the page.
Yeah, I can't add you because I'm not the administrator.
Okay.
Lizzie, it's for course rep too. Lizzie, it's for course rep.
But he's saying that we should are we all on the page?
No, he was talking about the course rep. So you contact Enoch. Any information that he puts there, Enoch will put it on our page.
All right. Okay.
If you're not on your main page, he'll put you there. That's what I mean. Yeah. Thank you so much. But my number is there.
Absolutely.
All right.
Auntie Vic.
Yes, Lizzie.
Na ose minko didimbra na mebo ade a meti minko na menti ase.
So yeah, na meti kono maduro na bra.
Oh, me yare mo but Me ame mom, but meeting who gra me one.
Ah,
Na
no, see,
masan so ko.
anti compliance. So be di na wati. We are no akoko.
Me nti asie na masan so ko. Huh? O ya me be frɛ wa nwumere yi na wa kyerɛ me bibia. What is?
Nya metumi
Ante
akyerɛ
be.
ne deɛ mɛkyerɛ.
Ante be.
Yes,
Ante be.
Lizzie. Lizzie.
Esi me frɛ wa nwumere yi na wa kyerɛ me nyama ni
Lizzie.
bi ase wa. Yes.
Ɛna me say.
Mhm. What's today?
When you frame me backstage.
All right. Bye bye. Mhm.